In this video, we're going to be talking about rates of change and behavior of graphs. So what we're going to do today is we're going to compute the average rate of change of a function, given its equation, table, and graph for specific points. Then we're going to do the same thing, but for an abstract interval, where we don't have specific points, but rather interval placements. Then we're going to analyze the graph of a function to determine the extrema, intervals of increase and decrease, intervals of concavity, and points of inflection. So we're going to start with rate of change. So suppose we have some function k of x, and we only know 2 points of the function. So let's say we know these 2 coordinate points, 2, 1, and 6, 9. That's all we know. Can we make an educated guess about the other points on the function? Certainly they could go all over the place, right? But can we come up with sort of a pattern that we could make an assumption that the function is doing over that space? So what you could do is think about how much you expect the function to change in y values per x value. So you could think of it as the change in y over the change in x. So what I'm really saying here is as I go over on the x-axis 1 unit, I'm going to go up on the y-axis 2 units, right? Change in y per change in x, okay? So I'm just going to be adding 2 to all of these y values and taking them for a ride. And they're going to slide up the y-axis to the appropriate places. And we see here that this pattern is actually not an unfair assumption about the behavior of the function over that space. Now, certainly it could be doing something crazy in between those points, but for right now, we could think of that as the general change of the function over time, our x value. Okay. So another way we could even think about this, what we're really doing here, it doesn't look like we're doing this, but what we're really doing here is if we drew a line between these 2 points and we just situated the y values at the particular x values over that space, we see that we've still come up with those same estimates, okay, from a less analytical standpoint. This is what we call a secant line. And what we saw from the table, its slope is the rate of change of the function over the specified interval. So if we look at the formula that we have here, right, something that we were given in high school and we sort of tepidly just had to assume was the case, what we're really doing is we're finding the delta, the change in the y values, and we're dividing it by the change in the x values in the hopes of finding how high up the y-axis we're going to go for every unit we move over on the x-axis. Okay, and that's really what we computed here. So a rate of change describes how the output quantity changes in relation to the input quantity. The units of change are output units per input units, okay? So y values per x values, right? What's happening? So let's start with this function here. We're going to calculate the rate of change of this function over the interval -1, 5. I'm going to go ahead and give you a second to try this on your own first. Mind that those vertical lines actually represent an absolute value function, which is prerequisite knowledge for the course, so you should know how to work with these. If not, that's all right. Take a second to review them after the lesson. So the first thing we're going to do in our procedure is compute the coordinate pairs. Okay, so we know the x values. Now we need to find the y values. Okay, take a second and find those if you haven't already. All right, now we're going to plug the x values in. Obviously, when I say take a second, that's going to mean pausing the video. I certainly don't expect you to do it that quickly. So we're going to plug our -1 in. We get 3 times the absolute value of -5 plus 1. Absolute value of -5 is 5. And I get 16. So my y value is 16 here. Same thing here. Okay, we plug this in, and we end up with 4. So now we have these 2 coordinate pairs, which is kind of nice. Now I'm going to use the rate of change formula, okay, our slope formula. y2 minus y1 over x2 minus x1. Okay. -2. Okay, so that's my rate of change. My rate of change for this of this function over the interval -1 to 5 is -2. So let's summarize rate of change. What is it? The rate of change of a function tells us the rate at which our y value changes with respect to x. How do you calculate it? Well, use the rate of change formula. If I'm given these two coordinates, I pretty much have everything I need. So from a table, in order to get these coordinates, all I would need to do is use the endpoints of the table for the particular interval, obviously, to get those coordinate pairs. From the graph, I would just look at the graph and get the coordinates from there. I may have to do some estimating for that, but that's okay. And then from the equation, I would need to plug those x values in to find the particular y values. Ultimately, what I'm really doing is I'm asking you to find two coordinate pairs, and I'm asking you to do a subtraction and a division. It's really what you're asked to do here, mathematically. So we're going to determine the rate of change of f of x over the interval 2 to 2k. Where does this k come from? This is that abstract interval that we were talking about for lesson objective 2. I want you to pause the video, and I want you to see how far into this you can get on your own. Okay, start with computing the coordinate pairs. All right, so let's begin with the coordinate pairs. We know we've got 2, so I'm just going to go ahead and plug 2 into the original function. Observe that the negative is not going inside of those parentheses. That's really important. And I get 5. That's great. And now I'm going to put 2k in the function, and I'm going to square that. So I end up with -4k squared plus 9. That's a weird y value. And for most folks, when they're looking at this, they're going to think, well, I'm not done yet. I mean, there's obviously more I have to do. Nope. We plug in 2k, that's what comes out. That's our output value. And now I'm going to do the same thing that I did before. I'm going to use the rate of change formula, y2 minus y1 over x2 minus x1. Okay. And so I get that 4k squared plus 9 minus 5 over 2k minus 2. So let's do some simplification here. And I get -4k squared plus 4 divided by 2k minus 2. And you'd think we're done here. But what you're going to want to try and do is simplify and factor. So I'm going to go ahead and factor out a -4 from the numerator and a 2 from the denominator. And I get -4k squared minus 1 over 2k minus 1. If you need to review factoring, make sure that you reach out to me so that I can point you to particular resources. Now, k squared minus 1. This right here should be jumping out at you. This can be factored again. Okay, the simplify as needed. This is going to be the tricky part for this course. So we're going to factor this k squared minus 1 to k plus 1, k minus 1. That's a difference of squares. If you need to look that up, if you need to refer to that, make sure that you do that. That's called a difference of squares binomial. Okay, make sure that you research that if this isn't immediately familiar to you. So the k minus 1s are going to cancel, which is really nice. The 4 and the 2 are going to reduce, so the 4 just becomes a 2. And I end up with -2, k plus 1. If you want to, you can distribute the the -2. That's fine. Doesn't really add or take anything away from the solution. And Lumen is prepared for you to input either. Okay, Lumen is totally fine with either. Now you're going to determine the rate of change over the interval 6 to 6 plus h. This is going to require a lot of algebraic handiwork, particularly as it pertains to fractions. If you need to look up particular things, I'll let you know what it is you need to look up. Okay. So we start with organizing our coordinate pairs. Okay, we plug 6 in, 6 minus 3, that's 3, boom, 1/3 is my y value, no problem. Now we do 6 plus h minus 3. Well, that's just going to be 3 plus h. I get these the y value of 1 over 3 plus h. Now I've got these two coordinates. So I'm going to use my slope formula. Okay. y2 minus y1 over x2 minus x1. I get 1 over 3 plus h minus 1/3 over 6 plus h minus 6. All right, before I dive into the numerator, let's just look at the very bottom. 6 plus h minus 6. I see that those 6's are going to cancel out really nicely. So now I'm going to go ahead and take that numerator and get those denominators to be the same. So I'm going to use my common denominator between 3 and 3 plus h is 3 times 3 plus h. So I need to give this first term here a 3, which is what I did here. And I need to give this second term here a 3 plus h, which is what I did here. I can't just give it to them willy-nilly. If I give a 3 to this first term in the denominator, I have to give a 3 to the numerator. Effectively, we're just multiplying by 1, which we can do anytime we want. Right. And now keep in mind, I'm also going to go ahead and distribute this negative through just to keep myself buttoned up algebraically. And so then I end up with 3 as my numerator, 3 minus h over 3 times 3 plus h over h. Now this over h, in a world without division, we can multiply by reciprocals. So just to make life easier, I'm going to go ahead and cancel out these 3's first. And then instead of dividing by h, I'm going to multiply by 1 over h. Okay, and I'll definitely have some extra sort of video materials for reviewing this, but this is prerequisite knowledge. This was the kind of stuff that you addressed in TE 7. So you do need to know how to work with this. Now from here, I see the h's cancel, which is kind of nice. And so now I end up with, 1 over, or negative 1 over 3 times 3 plus h. Again, if you want to distribute the 3, you can do that. But my final answer is going to be one of these two iterations of the same algebraic expression. Okay, it's the same thing. So if you need to review how to do this exactly, what you can do is spend a little bit of time on YouTube and look up simplifying. I'm writing this out so that you have something to look up. Simplifying rational expressions. All right. Simplifying rational expressions. Really take the time to look that over if you need to research the prerequisite that you need for this particular lesson. Now let's talk about intervals of increase and decrease for a function's graph. I think you'll find this to be much more intuitive and a lot more straightforward. There's certainly no real algebraic heavy lifting that you're doing for these. This definition is very rigorous, but it is really not intuitive. So here's the way I'm thinking about it. Give me 2 points, right? We'll start at A on the x-axis. And what I'm going to say is, as I go to the right on the x-axis, if I'm also going up on the y-axis in that journey, then that particular space is an interval of increase. That's what this definition is saying. Okay. In a similar ilk, again, this definition is really rigorous, but really not intuitive. As I go to the right on the x-axis, if I find that I'm going down on the y-axis as well, then that particular space is going to be representative of an interval of decrease. Okay? So let's consider this graph here. You're going to use interval notation, which is addressed in 1.2. It is prerequisite knowledge for the course, but make sure that you're taking a look at the interval notation that you see in 1.2 for domain of a function, just so that you have that as a frame of reference. What I want you to do is write out the intervals of increase and the intervals of decrease. Where am I going up on the graph as I go to the right, and where am I going down as I go to the right on the graph? All right, pause the video and try and write these out on your own. If you don't remember interval notation, or you feel a little shaky with it, that's okay. Just write it out with words, okay? All right, let's start with our intervals of increase. Okay, I see here that this is where something is starting and something is ending. Okay, so here's an interval of increase. As I go to the right, I'm going up. Now, where did that start? Technically, it started at negative infinity because it started all the way over here to the left. It's not negative infinity because I started at the bottom. I didn't start at the bottom. I started at the left, okay? And I'm going all the way up to 2 on the x-axis, okay? And that's where I stop going uphill. Now, at this point here, if you notice, I didn't put a bracket here. The reason I didn't put a bracket is because at that particular point, I am not actually increasing. I'm not actually doing anything. I'm stopping. I'm not going uphill anymore. I'm at the top of the hill. So I don't include the 0.2. This is an interval of decrease, okay? It starts at 2 and it goes all the way to the right. So it's always going down as I go to the right. So it's important that I note that this is actually going to be going to positive infinity. Some students are going to say negative infinity because it's going down, but up and down has nothing to do implicitly with left or right. Okay, so those are our intervals of increase and decrease. Pause the video and go ahead and write these out. All right, let's start with our intervals. Let's start by identifying where intervals are starting and stopping. So I've got these points here. This is where I'm either cresting a hill or I'm coming to the bottom of a valley. Okay. So intervals of increase, this is an increase, definitely. Right? I'm starting at negative infinity because it's all the way to the left, and I'm stopping at x equals 0. Again, it's not a hard stop at 0. I'm not including 0. Okay, so make sure that you're using parentheses for that. This is also an interval of increase. It looks like I'm starting at 2, and then I go up to 4. All right, now we're always going left to right, right? This is my interval of decrease. I'm starting at 0, and I'm stopping at 2. And my next interval of decrease, I'm starting at 4, and I'm going down all the way to the right to positive infinity. Okay. Now, intervals of concavity. Concavity is kind of a weird thing. What concavity is it's the rate of change of the rate of change. How is the rate of change changing? It's kind of a strange thing to think about, but take a look at these two companies. Company A and Company B are both showing an interval of increase. But let's suppose I was getting ready to invest. Which company would I much rather be investing in, Company A or Company B? If you said Company B, that's a prudent financial decision, generally. Because as I see that both companies, I mean, they're still sound investments over the short term, but Company B is setting up to do something crazy over time, whereas Company A looks like it's starting to kind of plane off a little bit. Both of these things are increasing, but obviously there's something else going on here. So it's really important that we have alternate vocabulary for this relationship. This is called concavity. So if I look at the particular tables representing sales, if I look at Company A, first I'm increasing by 5, then I'm increasing by 2.1, then I'm increasing by 1.6, then I'm increasing by 1.3. All right. Now, I see that the rate of change, that these rates of change from 5 to 2.1, that's going down. From 2.1 to 1.6, that's also going down. From 1.6 to 1.3, that's also going down. So I see that the amount I'm growing is decreasing over time. Here, I'm going up by 0.5, now I'm going up by 1.5, now I'm going up by 2.5, now I'm going up by 3.5. What's happening here is my rate of change is increasing. It's getting bigger. I'm adding more to the investment as time goes on. So, how do we discuss the difference in these relationships? They're both increasing, but one is increasing at a decreasing rate, whereas the other one is increasing at an increasing rate. So this graph, I think, or this picture, I think, does a really good job of demonstrating what's happening to the graph over time. So here we see Company B, and here we see Company A. Okay. Now, all of this was just to set up vocabulary of concavity. When we're actually looking at concavity, it's quite literally just looking for smiley and frowny faces. Okay. This is an example of concave up. This is an example of concave down. Okay. The rate of change is increasing. so it's concave up. The rate of change is decreasing, so it's concave down. Smiley face and frowny face. So we've got a function that's concave up if the rate of change is increasing, a function is concave down if the rate of change is decreasing, and the space where a function changes from concave up to concave down is called an inflection point. So this is another demonstration of what it is we're looking at here. There's two different ways that we can be concave down. We could be concave down and increasing, or concave down and decreasing. We can also be concave up and increasing, concave up and decreasing. So ultimately, any form of these shapes, right? This is our concave down and increasing, concave down and decreasing, concave up and decreasing, concave up and increasing. Okay, so ultimately there's this kind of pattern. So what I want to do here is work out the intervals of concavity of a function's graph. I'm not asking when is it increasing or when is it decreasing. I'm asking when do I see smiley faces and when do I see frowny faces. Okay, so we're going to start with the frowny faces. Pause the video and try it for yourself. Just as a note, the points of inflection are probably going to look a little different just based on where we decide to put them. Lumen is prepared for some rounded values. Okay, so we start with our points of inflection. It looks roughly that this is about where it is, where our frowny faces and smiley faces are touching. So there's our frowny face. Okay, we've got another frowny face here, and we've got our smiley face. Now I want to know when are these things happening. So for this frowny face, it's starting all the way to the left. Again, not because it's going down, but because it's all the way to the left. I'm going to run from negative infinity up to 1 on the x-axis, always on the x-axis. Okay, my next concave down interval is going to start at 3, and it's going to be concave down all the way to the right. So that's going to be positive infinity. The face in the middle, sandwiched between these two sad faces, we're going to start being concave up at 1. Now keep in mind, I'm not using a bracket here because at that x value of 1, I'm neither concave up nor concave down. I'm changing. And I'm going to stop being concave up at about 3. Now my points of inflection, those are my coordinate pairs. Okay, so these are where I decided my points of inflection were. Make sure you write those as coordinate pairs. Again, you're going to see rounding. Lumen is prepared for not exactly one particular place, but a space that makes sense as a point of inflection. When you get to calculus, you'll be finding the exact points of inflection, but that is a crisis for another day. Pause the video and try again with your concave down, concave up, and points of inflection. Okay. So here's our points of inflection. Okay, our concave down intervals, -2 to 4. Concave up, we have negative infinity to -2, and then 4 to positive infinity. In Lumen, you will use a big uppercase U in between these spaces. Okay, that means union. All right. Our points of inflection are the coordinate pairs. Okay, we've got these coordinate pairs here. We said -2, 2, and 4, -6. Okay, and that's our 1.3 lesson. All right, if you need to be pausing the lesson throughout practicing particular problems, then by all means do that, just because there's a lot of different smaller skills represented in this lesson.